Thank you. So track one, example one, we're talking about with wave equation analysis for construction control. So on track one, example one, what we're going to do here is we're going to follow the design and construction steps to implement the pile design. We're going to select a resistance factor to estimate contract pile length. Estimate the target nominal pile driving resistance. This example will include the considerations for pile setup. So we're going to have a cohesive soil, and then we're going to go through these steps. So these are the steps we had from before. So just to reiterate, the preliminary design engineer is going to come up with the type, size, and location for the bridge. Then the geotechnical or soils engineer, he's going to go out and get some data and come up with some foundation recommendations. The final design engineer makes the determination what the pile arrangement, loads, and other design requirements are. An estimated nominal geotechnical resistance is established. We come up with the resistance factors and the estimated pile lengths based on the construction control and the type of soil we have. We come up with the required nominal pile resistance then to come up with a pile length for pay lengths for the contract. We also establish what the targets are. What we said was at end of drive is going to be a lower capacity than after, say, 7 days after end of drive. The nominal power resistance is based on what's happening after the setup has occurred. We have to come up with some notes to put on the plans, make sure we've checked everything, everything's kosher, move into construction. We need bearing graphs in order to monitor when the piles are acceptable, and we got to go and monitor the actual pile driving, record the resistance, and resolve any issues. So here we go. We have an integral abutment. It's going to be on H piles, cohesive soils with setup. We have a wave equation analysis for construction control. So first step is we have a situation. So we're going to turn around and have a situation here, 120 foot, no skew, integral abutments, single row of piles because we're on integral abutments here. We have a soft clay up in here. We have, and we'll see that in a second. We got sand and we got some till below. So we got an H pile, span lengths less than 130 feet, so we don't need to pre-bore per Iowa DOT requirements. Bottom of footer at 433. Notice that's the bottom of footer here. We have a soft silty clay directly below the footer below the bottom of footer for 6 feet, 9 foot of sand, and we got a firm glacial clay underneath. In here, the foundation engineer, the soils design engineer came up with recommending that we tip out in the till, in the glacial clay. Normal driving resistances, SRL1 structural resistance level, so it's 6 KSI, and there's no drivability concerns. We don't have any special concerns about global stability, settlement, laterally loading. Here's the pile arrangement in the footer for the abutments. Notice we got 7 piles across on the abutments and 1 pile behind underneath each of the elephant ears here. 128 kips, strength 1, limit state. So just to reiterate here, when we say strength 1, does everybody in the room understand with LRFD with strength limit state versus service limit state? No. That's good. We're all going to slow down to your speed because it's important that everybody understand it. For those that do, this will be a good refresher. Let me draw you a sketch. We keep putting new names to old ideas. So we're going to increase load on the pile, increasing this direction. In this direction, we're going to have pile displacement. And as we load up the pile, eventually she's going to plunge like this, right? Call it service limit state design, allowable stress design, working stress design, load factor, load and resistance factor. Doesn't matter. This behavior occurs. We would load up the pile and that's what happens. So what happens is Davison's method, they look for the point where there's most curvature in here. They run it out this way and they say right there, that's the nominal resistance, R sub n. That's the ultimate, that's what the pile is good for, no matter what you call it. Now, somewhere back in here, say, right in there is the factored load. So that's gamma Q, or the strength 1, if we're going to do it. Strength limit state, in this case we're calling strength 1. That's strength 1, all it means is we have no high winds, no earthquake, no unusual loads. It's just a routine everyday loading. The service load is probably right about here. So what we have is we have a service load. We have a 1.0 times the service load. We got a load factor of 1. So that's the actual. If I would actually put a load cell on that and measure what the actual load is from the bridge, that's what it is at the service state. So the important thing to note is, are we talking about this point here, or this point here as we load up the pile? Does that make sense? In this case, if we were doing is a typical bridge where we have a dead load to live load ratio of 3 to 2 in here, and we sum them out, this is where this 1.45 came from. It's just a generic. All that means is that this strength is approximately 50% more, well, it's 0.45 more than the service load. That's all it means. It's just a way to put and the factor of safety gets you between here and here traditionally. This is what we've always done. And all that is gamma over the resistance factor. So it's a load factor divided by the resistance factor. And that's LRFD 101. Does that make sense to everybody? So when we talk about strength 1, we're here on this curve. So don't get yourself all twisted and confused when we start going around factors of safety and things are going up and down. Just visualize where on this curve are you. And that way, if you look at it from that way, maybe that'll help to visualize how to tie what you used to do versus what you're going to be doing from here on out. So we have a strength 1 of 128 kips. So based on that, we have a service load roughly 80 kips per pile, right? Based on that discussion. Okay, and then next is we have no uplift, no down drag, no scour. So whatever embedment we have below the bottom of footer is all contributing to resisting that load. And then we're going to do a wave equation analysis. That just means it's a little bit more predictable than the ENR, which means basically I don't need as much. I can reduce the lengths. Okay, so now we're coming here on step 4. This is right out of the blue book. And so as we go through this, I want to take you to your manuals because I find it seems like everybody's in tune here today. If you look in volume 4, page 137. So this is the chart that's on the screen. So when you're going through, you might want to make a notebook. In your notebook, just go look at that page. It's where you're going to find it in the volume. So what happens here is we had a soft silty clay up at the top, then we had a silty sand, and then a till below. If we just go back, there it is right there. So we had the soft clay at the top right in here, with the pink, the sand is in the yellow, and the till here is in white. So the soft silty clay in here, we came across, it was soft, and we come across, and we come down from the steel H-piling HP10s, and we're getting this 0.8. And we're going here with the silty sands. It was a loose sand in here with a blow count of 8, and so we got 1.2. And in the same token with the firm glacial clays, it's a medium stiff in here, and so we had 2.8 within a depth of 30 feet below the ground surface, and at greater depths it was 3.2, which is the number in brackets. And this will just blow up the different views just so it enhances it. You'll notice the note at the bottom here on the table, which clarifies about above and below that 30-foot point level. So now we look at this page here on the screen. So that's going to now place you in your workbook, the top frame on page 4 for topic 7. And you notice we're posting here. So this is a simple way just to record the key numbers down, what the average blow counts were, what the thickness of the stratum is, which one it is. Notice for stratum 3, it's broken into A and B, depending on whether you're within 30 foot of the ground surface or deeper, and the appropriate resistances in kips per foot from the Blue Book. We'll be coming back to this in a moment. Okay, now we need to pick off a resistance factor. And in here now, we have that sand. If we go back here, we got a little bit of sand. Remember, there was that 70% rule. So the question is, for our total embedded length, is that 9 foot going to be more or less than 30% of the available length? If it's going to be more than 30% of the embedded length, then it's going to be mixed soil. If it's less, which means there's more than 70% cohesive soils, then it's going to be a clay site, not as a cohesive. Which way it goes is depending on what the total length is. So what we want to do here, if we're going to use, for a theoretical analysis, we're going to get our nominal capacities, our ultimate capacities from the Iowa Blue Book. Keep in mind what the Iowa Blue Book on this chart here is predicting this point here, right, for the embedded length. That's what's important to remember. Historically, what it did before was give you the service capacity, which was here, right? And if we were using a factor of safety of 2.2 for wave equation, then if this was 220, then this would be 100 ton right here. It's just whatever the ultimate is divided by 2.2. Now it's giving you the ultimate or nominal capacity as the number coming out of that Blue Book. So what happens is we're getting a nominal or ultimate capacity out of the Blue Book. We are going to use the wave equation analysis, so it's going to be one of these 4 rows coming across. We said we're not going to do a PDA or CAPWAP analysis. We're not going to do a mandatory retap at 3 days. We're not going to do a static load test. So by default, it's this row right here. Notice here we have a resistance factor of 0.65 if it's cohesive soil or mixed soil. It just happens to be the same number. Notice that there's no resistance factors at this point for end of drive and setup, because all we're interested in at this point is to estimate a pile length. So we pick that row. There's the values. There's just an exploded view. So here we go. It's 0.65 for cohesive, 0.65 for the mixed. And the non-cohesive, in this case, is not, it's here for completeness, but it's not, by inspection, it's not going to be that one. Okay, and then so we're by inspection, we're thinking it's going to be more than 70% in cohesive soil, but we'll see. Okay, so now we go here, this chart here. So for reference, if you go on volume 4 on page 139, Okay, you might want to put a note in your workbook. If you would just flip to volume 4, page 139, that's where you're going to find that screen. And the key then is for the non-cohesive are the A1, A2, and A3 soils. Basically the loams, the sandy loams, is basically beach sand or coarser in terms of granular soils. The cohesive then is the clays and the silts, and the clayey or silty loam material. The A4, 5, 6, and 7 material is classically what it is. So now we need to come up with a pile length. So what we're doing here, keep in mind from the Blue Book value, right, we're here, that means it's the ultimate, right? Now we need to know what if we cut the resistance factor, right? So this spread here, to come up with it, has got this resistance factor built into the denominator if this was a factor of safety. So what we got to do is we got to take that factored load of 128 divided by the resistance factor in order to come up with this 197 kips of nominal capacity. Does that make sense? If we took this equation right here, right, here's the 128 is the Q right here, right? Is gamma Q, summed all the different loads, dead loads, live loads, the whole bit. Got to take this resistance factor, drop it in under the denominator in order to get the nominal resistance. That's all we do, is just peel the resistance factor and dropped it in onto the left side of the equation. So in here now you get the 128 divided by the 0.65 is 197. Remember we said there's no down drag load. If there was, we'd be plugging that in here and we would have a number here. And so what happens is when we do that, that's what we calculated it out to be. Okay, now this page here, we're now at the top of page 6. Now you're going to have this, let's keep this in front of you on your desk, but I'm going to flip back to the picture because I'm a graphic kind of person here. So I'm going to go back, so we have this picture in front of us, this chart right here. Okay, so in the first line on the top screen on page 6 of topic 7, it says that D at 0 at the ground surface, or at the bottom of the footer that is 0 feet. And the resistance at that point obviously is 0. Now, it's 6 feet, which means it's 6 foot below the bottom of footer. Here it is right here, was that soft silty clay. We had an average blow count of 4 and 0.8. So you'll notice in the equation there, it says to take the 0.8 times the thickness, which is 6, and that's going to give us 4.8. Now, the next point down then is the bottom of the sand. So you'll see the next line on that frame in the top of page 6 was 6 plus 9, which is 15. There it is, 6 plus 9. And at that point, we take the sum from the previous one, which was 4.8, and we add to it 9 feet times the 1.2. And you'll see it in there, 9 times 1.2, which is 10.8 kips. So 4.8 plus 10.8 is 15.6. The next point down was where we get down to this 30-foot depth. So now we're going to have the 15 plus the 8 right here. So now that pushes us down to 23-foot depth below the bottom of footer. We're going to carry down the 15.6 that we summed from before, and we're going to add to it 2.8 right here times the 8-foot thickness. And that's going to give us 22.4. So 15.6 from before plus the 22.4 gives us 38 kips. Then down to the final depth down here, then 65 foot deeper, then what we're going to have is the 23, which got us down to the top of that, plus the 65, brought us down to 88 foot depth. And we're going to add to it The 65 feet times the 3.2 gives us 208, and 38 from before plus 208 gives us 246. All this is just to generate a bunch of points to generate an XY plot. What is the resistance gain versus depth? So let me move the frames forward here, and you'll see that in the next frame. So if I plot those points, then I get a curve like this. That's all it means. Now remember what we said was the nominal resistance is what the blue brick is predicting is all the way out here, right? And we said that was the 128 divided by the resistance factor of 0.65, which is the 197. And so what happens is we got to come across till we get to 197, then come down, and then go across, and we can estimate our embedment length below bottom of footer. So there's the 197. We come down, we go across, and we get 73 feet. Now remember, the 73 feet is the amount of embedment below the bottom of footer. So there's the embedment. We're going to have 1 foot cut off because we never can install these piles right to the T. Lots of things happen, so we're going to have a 1 foot throwaway in there cut off. Plus we're going to have some embedment in the footer itself. So I need 76 feet of steel pile. Now this is to estimate a length. Piling typically comes in 5 foot length increments. So what happens here is, say you order, if you order an oddball length, they're going to sell it to you as if it was 75. If you wanted 74 foot delivered to the job, then what they'll do is they'll buy 75, throw a foot away to cut it to 74, then they use the scrap to buy beer money for the pile drivers. I guarantee you it does happen that way. You don't think the scrap steel goes anywhere but into their beer fund. So that's where it goes. So here it is, 75 feet. Okay, now what we got to do is, remember we had that 70% rule that we had to verify. So what we're going to do here is, since we're going to order 75 footers and we're going to put 2 foot into the footer, that takes us down to 73. We got to account for the cutoff, that's 72. So we have 72 foot of pile that's going in the ground below the bottom of footer. That's right here. Minus the 9 foot of sand, divided by the total 72, and we have 88%. So there's 88% of the pile in cohesive soil that's embedded. Does that make sense? So now we validated, yes, the 70% is true. So now that we've gotten out of the design, I guess the only other thing to remind here, if we went back when we got the resistance factors, right, you got to remember to go to the correct chart in here. And so the resistance factors on page 141 in volume 4. You'll notice in here there's 2 tables, C1 and C2. One was for piling in compression, which is table C1 at the top of the page. C2 is for if we have tension piles. So that's the one we use for design and contract length. That's where we were a few minutes ago. That's the first half of the puzzle. Okay, then what happens on page 142, now we come to the flip side, how to set these targets for construction control. We don't want to get these 2 tables mixed up what the purpose is. So the key to pay attention to is this construction control right here. Okay, so now what happens here is that we now have this issue, the Iowa Blue Book here. We have the WEEP, which is one of these 4 rows. We went through this before. We're not doing PDA. We're not doing a mandatory retaps, not doing a mandatory static pile load test. Defaults to this row right here. Notice here now, this fee, there was a 0.65 before, it's gone. Because when we're doing construction controls, what we're doing is we're wanting to target end of drive as well as what is the benefits from the setup. So these resistance factors here are the ones that apply. And we already validated this is the overall embedment is classified as cohesive. So these 2 values right here are the ones that are going to be of interest. And there it is. It's just going to paint them up. It'll blow it up for us. And that's what it is. Okay, so now just for completeness, it listed all these, but the reality is we know it's the cohesive soils right here. These are just the different values. So now we're scaling back is the key buzzwords on this screen here in order to know what's going on at end of drive. And so now here's just the overall equation here. It's the same as we had on the board, on the wall over there. And we had a native value of 1. It's just an importance factor. Other than a special project or a bridge of special importance, I would assume the load modifiers for all your projects are probably going to be 1. Now we come to the nominal driving resistance. Okay, so what happens here, now we have the resistance split up both between end of drive and what's happening with fee setup in here. Okay, and then we had 128 kips of factored load. That was from before, no down drag, and we had the setup ratio. Now the setup ratio comes from a plot. That's right here. Now this plot in volume 4 is on page 143. And what you're going to notice in page 143 is slightly different here. It's the same plots. What's different is on page 143 also has set up what happens at 30 days. We ought to take a look at this plot for a minute. Notice that at the lower SPT values, F setup is higher. Regardless of whether it's, here's 1 day is the short dash line, 3 days the longer dash, 7 days is a solid line on here. So this line right here is 1 day. Here's the setup for 3 days and 7 days. And as blow counts get lower, which means the clay is getting softer, then the setup is higher. Also notice that the difference in the spread between the lines from 1 day to 3 days is only 2 days incremental increase, right? And notice that that spread's larger than what's happening between 3 days and 7 days. So this is twice the amount of time change here, and it's even smaller. The lesson learned there is most of our setup occurs in the first day or two. So now what happens here is we got to take the average SPT value for the cohesive soils only. We ignore the granular soil that we're penetrating through. And what is the average, what it was? So we had 6 feet of the upper clays in here, the silty clays, at an average blow count of 4. Plus we had the 8 feet that was that layer 3A that was in here of 11 blows. And then we have the remainder in the denser materials. So we've taken the 72 foot minus the 23 foot of penetration to get here, average blow count of 12, and we're only taking it over the depth that it's in clay, and we got an average blow count of 11. So we've ignored the sand entirely in this calculation. So we come in here at 11 blows, we're going to come up, and we're going to pick off what these different values are. And that'll appear now. So what's happening is at 1 day we expect a setup factor of 1.48, 3 days of 1.55, and 7 days of 1.61. So we're going to come back to this equation. And notice here we're filling in the factored load of 128. We had the fee factor at end of drive of 0.65. We had a fee setup of 0.2. And that value from the chart just a moment ago for 7 days was 1.61. When I take and run the calculations out for the denominator, I get 0.77. Now the interesting thing to note is currently in the interim manual for the DOT, this value is 0.725. And now that we're taking advantage of this setup, we're ending up with higher resistance factors than what we've been using. And the meaning of that is that we're ending up with shorter Powlex. Right? The higher that number is, the lower the length will be. Shorter it will be. And then when I take the 128 divided by that, I get 166 kips or 83 tons. Okay, now that's the target at end of drive. At 7 days, it's going to, that's where what that, well, that's what we have right here, is 83 tons. So now what happens here at 1 day, notice that we would take the end of drive, the 83 tons is just shown as kips. There's 166 kips, and we have that F set up in here, and we have the different ones for the different points. Notice that 166 times 1.48 is 246. But remember here from structurally, the structural engineer said, I only need the 128 divided by the 0.65, right? Which is 197 kips. He doesn't care how you get here. As long as we can provide you 197 kips of capacity, it doesn't matter how. If we can provide you this much, mission accomplished, we're done. So this is going to be an either or. So it's smaller of. Either this or the 197 is a threshold. Either will get us there. So in this case, as long as we achieve 99 tons, we've accomplished everything we're shooting for. Does that make sense? You've got to think about what we're after in the end result. So now we need some design notes here. The other thing I wanted to point out here, just so that it's clear, back here on this setup, remember about the pore water pressure in here? We said that remember that plot earlier? It was one of the earlier presentations that when we first drive the pile, then we have a pore water pressure dissipation, and with that pore water dissipation, we're getting this pile set up. So if we had a bag of chips here, and say the pile is driving down, or I load it up with a footing, and so that when I press on this, does the volume of the bag change? Or does the shape of the bag change? So all I'm causing the soil to do is to move around, but nothing has physically changed, right? That's a really important concept in soil mechanics overall. Okay, so then where do we get the strength gain? Well, poke a little hole. What happens is the clay it takes a long time for pore water to dissipate. So as it dissipates, then that fluid, whether it's air or water, starts to dissipate until the grains of the soil's starting to take over. That's what's happening with the setup. It's no different than what we're doing with spread footings or a half dozen other things in soil mechanics. Does that make sense? And if we get into organic soils and secondary compression, that gets off target, but then it's crushing, right? The skeleton starts to crush. Now, since I opened the bag, why don't we can eat some munchies. So now that we came up with some numbers here, we need to create some notes for the plans. The first step is we need a record of what we did, right? I mean, we've all been through it where we end up having to retrofit a bridge. Instead of HS20 loads for truck traffic, all of a sudden somebody said, oh, we want HS25s. We want permit vehicles. Everything seems to grow with time. It used to be a tandem truck was all we designed for. Now we got 5, 6 axles at times. So what happens here is we need a record so that later down the road, the people that follow behind us can deal with this bridge later. So what happens here, we had a contract length. That's of interest. We had 75 footers at the abutment. We need to know it was based on, we were thinking about cohesive soils, and we needed to know we had a factored load that came out of the structural group of 128 kips, and that length was based on using a resistance factor in here of 0.65. The other piece of the record that we need to keep here is that we had the construction control in order to come up with it was based in here, the nominal axial, from a cohesive soil and a resistance factor of 0.77. The 0.77, if you recall, if we go back, is right here. In other words, it's after the setup has occurred, and it's this net value here is what's important. Now, we need another set of notes in order to tell the guys in the field how to implement this, right? The idea, we're going to go verify the pile is okay. We need to know, well, okay, so what constitutes okay? Well, what we need is at end of drive here, 83 tons. If you can get me 83 tons at end of drive, mission accomplished, we're happy, go ahead, put your footer in. If not, then we need to do some more. So what happens is, if we don't meet the 83 tons, then we're going to do a retap, if you recall from just before lunch. So if we go to do a retap, and based on what we had before, whether it's 1 day, 3 day, or 7 day, in this particular case, 99 ton was acceptable because it gave the structural engineer what he needed, because we got his capacity he needed here. Then what happens here is the contract length then should be driven as per plan unless the piles reach refusal. Construction control requires a WEEP analysis. Now, unless it reaches refusal, that comment came up earlier. Somebody was asking, especially like with scour. If I'm not mistaken, if you change from the contract length driven, you got to get permission. So, and then you got to consider like scour, right? You got to have a minimum embedment regardless. And that's on a one, you know, the idea is the contractor was hired to get the pile down, all of it down. Now, if you deviate, then you got to deal with it on an individual basis. Why did you get the refusal? And construction control requires a WEEP analysis and a bearing graph. Notice this is now in here. It's not a voluntary thing. It was expected, and these lengths were established based on that understanding. Does that make sense? Any questions with this? Any questions so far? This is a lot of material to kind of take in here.
You're saying in design you need 197 kits per pile. Right?
Correct. In design, we need 197 kips. And where that came from was from the structural side of the house. It says I got 128 kips, a factored load, which we said was, if we just took it and divided by the average load factor, is the service load, say in the neighborhood of 80 kips, right? And when we add in the resistance factor to get the nominal capacity, we needed 197. No matter what, as long as I provide enough resistance capacity that exceeds the demand.
So yeah, so we had your resistance capacity was, I'm looking for that number. What was that number?
The 99 tons, or the...
270, what was it, kips?
It was, you're talking about the 165?
You had the 246, 257, and the 267 after the setup.
Right.
So yeah, you're more than what's required, so that's why you're good.
That's correct. Yeah, so what happens is with setup, and the important thing to note here is, with setup, we're predicting capacities well in excess of the demand. That is not necessarily a bad thing. But at the construction stage, the real question is time is money. We don't want to sit, we don't need to wait for the 246. As long as we meet the structural demand, let's move forward. If we could move forward immediately, the contractor, the owner, everybody wants to move ahead. Any other questions? All right, so we got the notes on the drawings. Now we got to go and pull a few hairs out to make sure everything is all in order. Get the contract out on the street. We've got received bids. We've awarded the contract. And now the first thing the contractor's got to do is tell you what hammer he plans to use. And it's not just hammer, but he's got to tell you about his hammer and anvil. Usually they come in sets. Cushions can move all over the place though. So even though he keeps telling you, I use this hammer, which cushion are you using on this job? And the cushions change based on pile type and size. We have helmets in there that are fitted to work with a hammer in order to fit on a particular pile size. And so he's got to give you the specifics. And once he gives you the specifics now, here, now that you have the specifics, now you need to do a wave equation analysis based on the specifics. You can't do that in the office in advance because every contractor has his own hammer, his own cushion combinations. And it would be an endless myriad of combinations. So once you know who the contractor is, you have the data, and then you can run it out. Cam went through the WEEP analysis and showed you on the computer software. It looks a little scary at first, but it's really not bad. But the goal is to produce this bearing graph. And the idea behind the bearing graph is we're going to turn around and create, in this particular case, 3 separate curves on this graph. The idea being is that each curve represents a different stroke. So you see here's a 7, 8, and 9 foot strokes. So the green line here is the 7-foot stroke, 8 is the blue, 9 is here. If you have like 7.5-foot stroke, you can interpolate between the two. So what happens is you're going to drive the piles down to contract depth. When you complete driving it down, you're going to record and pay attention to what the blows per foot. On the way down, for bookkeeping purposes, you're going to track it blows per foot on the way down. But the key is what's happening when we get to the tip elevation. So say we had 40 blows per foot is what's happening at tip elevation. So we would come up. If we had a 7-foot stroke, we'd pick it off. In this case, it would be like 103 ton of capacity. If it was an 8-foot stroke, it's a different value. 9-foot stroke, it's a different value. And then the inspector would go up, across, record what that number is from the chart, and records it in his driving log. So he's going to record the stroke and blows. It's going to use that graph. And if it's not adequate, then we've got to come back and do a retap. So here's the driving log. Now in here, a comment came up yesterday is that this header needs to be modified a little bit to make it clearer, which will be done, in terms of what's happening with what's going on at end of drive versus the retaps. It's on the plans, but it probably should be written down on this log so that it matches the notes on the plans. In this log here, there's a pile number in the first column. What day it was driven is the next. The plan length is here. The length cutoff. In other words, it's not uncommon to see that the piles get driven down a little differently, and so we record how much we actually cut off. What the blows per foot was when we finished up. What the stroke was. In this case, it was like 7.5 feet here on that pile. And then what the driving resistance is, this is the value being plucked off this bearing graph here. The next columns over here have to do if we have to retap it. So on this particular example, we had 30 blows per foot at a 7-foot stroke, or I guess it was 7.5-foot stroke in here, if I'm looking here how it's interpolating between the two, and we got 88 tons of capacity. And we're done. Now, why were we done? Remember, we had a target capacity in here of 83 tons, right? So at end of drive. Remember, we said it was 83 at end of drive, but if we wanted to get the full capacity structural engineer at 7 days after the setup it is, then we needed the higher capacity, right? And we're relying on the setup to carry us the rest of the way. So since the 88 exceeds the 83, we would accept that pile. Does that make sense? Everybody okay with that? You comfortable with the idea of accepting a pile below what the structural engineer required? And because of the setup, right? You should say, no, I'm not comfortable with that. I don't believe in lip service. I like to touch and feel, and so we know that. How do you get that comfort? Retap it a day later After you do a couple projects, you'll convince yourself that setup is real. If you're not convinced, I suggest do something. Don't just believe me. You should believe in it. The setup is real, but initially, this is going to be a tough pill to swallow. But what this does, it gives you the mechanism to begin to count on it and to start to reflect it in your designs up front. So what happens is, we had a Blue Book nominal capacity, right? Remember, what is that? That's this point all the way out here now in the Blue Book. With the revisions, we're giving you this value. When we were doing allowable stress design, that Blue Book was giving you this value. It's still the same because the Blue Book before had a factor of safety in it. All we did was take this factor of safety, pushed it over to here. So it's exactly the same numbers you've always been using. It's just how are you looking at it. It's the same relationship. We're still using the Blue Book for the nominal or ultimate capacity. Nothing's changed there. The other comment I guess I could make is part of this investigation study was looking at a lot of different methods of analysis. We didn't just default to the Blue Book. We looked at a lot of different ones. The reason the Blue Book won out is because the department in its wisdom has been keeping tabs on pile load tests for a long time. The Blue Book was based on its own version of calibrating against those load test results. We're using the same raw data. We have more data now than we did when it was first developed back in the 60s and 70s, right? But still, there's enough history that it's still trending the same. So it's still valid to this day. We had a resistance factor. Remember that the resistance factor is a function of what construction control we're using, what type of soil, what limit state. We came up with a contract pile length, right? 75 feet, that includes the embedded length, the piece that we're cutting off, the embedded portion in the footer. We go into WEEP analysis for construction control. We had a net resistance factor at end of drive of 0.77. That was to estimate the lengths, right? Remember, what it is this is, remember when we calculated back here when we factored in the setup, which is higher than what we've been using as a default of 0.725 up till now. And what that should equate to is a shorter pile length. Target driving resistance, this is at end of drive of 83 tons. With retap, 99 tons. The 99 gets us to where we need in order to satisfy the structural engineer's need for demand. And that brings us to the end.